Hello everyone, welcome back to Clear Creek Solutions Hydrology Education videos. Today we're continuing our series regarding dams. We're going to be looking at the design of gravity dams and some of the things that need to be taken into account, some of the diagrams that are available there. Please like and subscribe to the channel to continue learning about hydrology education. We have numerous playlists on hydrology software, hydrology topics that may be relevant to you, so go ahead and check those out there. Prior to the middle of the 19th century, dams were designed by rule of thumb with little concern for the principles of mechanics and materials, and as a result, they were usually more massive than necessary, or often designed to be quite oversized. Pioneers in the field of improved design of gravity dams were the French engineer de Cizilly, the English scientist Rankine, and in the United States, Wegman. So we're going to go over the design of gravity dams. We had a previous hydrology education video describing different kinds of dams, so we have some gravity dams with some pictures here down below so you can get an idea of what they look like. If you want descriptions, go to that other video. But a gravity dam must be statically and dynamically stable, and the design must be such that stresses in the concrete do not exceed the allowable limits. To have a stable structure, the reactive forces developed by the rock and soil upon which the dam rests must be capable of balancing the active forces mentioned in this section. A carefully conducted geologic investigation should be one of the first steps in the design of a dam. The geologic investigation should include inspection of the rock outcrops and extensive underground exploration by means of test holes, core drilling, and geophysical methods. So when it comes to actually building the gravity dams, we need a good idea of what is the structural soil beneath the dam itself. What are we dealing with? Because that's going to determine the forces. It's going to determine the unit weight of the soil, what sort of materials we're going to need for the dam, because that's what it's going to be resting on in the end, just like any other structure. So some of the test holes should be large enough for a person to enter and inspect thoroughly. A simplified approach to the analysis of gravity dams based on elastic behavior of concrete is presented here in the slides. This approach is adequate for the design of small dams. It is also useful for preliminary design of large dams, though final design is generally accomplished through application of more sophisticated methods involving finite element procedures. So what about the structural stability of gravity dams? A free body diagram with a cross-section of a slice of a gravity dam. Although a gravity dam behaves almost as if it were a monolith, for purposes of the simplified analysis, it is assumed that each slice acts independently of adjoining slices. The forces shown are the weight of the dam W, the horizontal components of hydrostatic force H sub H, the vertical components of hydrostatic force H sub V, uplift U, ice pressure F sub I, the increased hydrostatic pressure caused by earthquakes E sub W, and the inertia force caused by the earthquake on the dam itself E sub D. The vectorial resultant of these forces is equal and opposite to R, the equilibriant, which is the effective force of the foundation of the base of the dam. A gravity dam may fail by sliding along a horizontal plane, by rotation about the toe, or by failure of the material itself. Failure may occur at the foundation plane or at any higher level in the dam. Sliding or shear failure will occur when the net horizontal force above any plane in the dam exceeds the shear resistance developed at that level. It is good construction practice to step the foundation of a dam to increase resistance to sliding. Overturning and excessive compressive stress can be avoided by selecting a cross-section of proper size and shape. Typical working stresses employing the design of concrete dams are about 600 psi or 4,000 kilonewtons per meter squared for compression and 0 psi for tension. Tensile stresses are avoided by keeping the resultant of all the forces within the middle third of the base. So you can see here a diagram of dam gravity analysis. We've got the headwater on the left, the weight of the dam, the heel and the toe. We have uplift pressure, of course, and then we have tailwater. So all these have to be taken into account. So you see on the upstream side where the pressure is actually being activated here, about 1/3 of the height up. You can see it takes a triangular force a diagram here. And H sub 3 is where the force is going to be acted, which is WH squared over 2 against the dam. Then, of course, we have earthquake loads, wave loads, ice loads, which are more minor loads, but also have to be taken into account during those different kinds of conditions. So we have to take into account the self-weight of the dam, which the material was built with, and of course the uplift load because there's going to be water. So between the water load and silt load, there's a lot to take into account when designing the gravity dam, but those are going to be the major forces. Before construction work in a river channel can be started, the stream flow must be diverted. In two-stage construction, the flow is diverted to one side of the channel by a cofferdam while work proceeds on the other side. After work on the lower portion while work proceeds in the other half of the channel. If geologic and topographic conditions are favorable, a tunnel of diversion channel may be used to convey the entire flow around the dam site. A tunnel is particularly advantageous if it will serve some useful purpose after completion of the dam. 4 50-foot circular concrete lined tunnels were used for diversion at Hoover Dam and later converted to outlet works. It is advantageous to schedule construction of the lower portion of a dam during low flow periods to minimize the diversion problem. The foundation must be excavated to solid rock before any concrete is poured. After excavation, cavities or faults in the underlying strata are sealed with concrete or grout. Frequently, a grout curtain is placed near the heel of the dam to reduce seepage and uplift. A grout of cement and water, sometimes mixed with a small amount of fine sand, is forced under pressure into holes drilled into the rock. So that's an overview of the design of gravity dams. We'll go more in depth with equations in our next video on gravity dams. We have a hydrology terms guide with outlines of 3 most popular kinds of hydrology modeling techniques. You can get that guide in the description down below, as well as check out our channel for other playlists regarding hydrology education, software modeling, and information regarding hydrology and water science. We thank you so much for watching. Anyways, we will see you guys next time.